So yeah, thank you, Obin, for inviting me to talk. Yeah, as you said, I graduated from Wisconsin in 23 and spent the past year at NASA Goddard with Christoph Keller and then Julie Nicely. I've been working on trying to kind of see whether machine learning could potentially emulate the adjoint of GeosChem for chemical data assimilation with the NASA GEOS modeling system. Yeah, it's been a kind of a crash course in data assimilation and atmospheric chemistry and learning geochem and all that. So, yeah, it's been a fun time and yeah, been learning a lot. But yeah, this is some of the kind of results we've had so far. Um, yeah, I'll just get into it. So, I think as all of us here are pretty familiar, accurate quantification of air quality is really important for assessing emissions, human health impacts, and how atmospheric chemistry might interact with climate as well. And for this purpose, NASA's Global Modeling and Assimilation Office, led by Christoph Keller and Emma Noland, have been developing GeoCF, provides 5-day forecasts of atmospheric gases and aerosols, around 290 species in all. It uses GEOS for meteorology and the GeoChem module for chemistry. And yeah, on the right is just an example of a GeoCF NO2 forecast. However, mainly due to the computational cost and difficulty of developing assimilation systems, GeoCF doesn't currently assimilate observations of atmospheric trace gases. So the broader kind of research slash technical question motivating my project has been how to conduct computationally efficient data assimilation to nudge GeoCF to real conditions that might not be captured by the emissions inventories and the chemistry of the model. And the kind of data assimilation method that we aim to use is 4D VAR, or that we aim to enable is 4D variational data assimilation. A key advantage of it is that it enables us to preserve the kind of chemical consistency of the model as opposed to something like ensemble Kalman filter. So I'm going to give a brief overview of 4D VAR. Yeah, some of us, I certainly wasn't very familiar with it, so I think this might be helpful for some of you guys. So yeah, first of all, we'll get kind of an initial concentration of chemical species from the prior assimilation time step at time zero, and then we'll get an initial model trajectory from GeoCF. And then within the specified assimilation window, we'll also have some satellite observations at future times in that window. And purpose of 4D VAR is to kind of find the optimal, I guess, middle ground between what the observations tell us and then what the model trajectory tells us as well. And then finding this optimal trajectory involves a process of iterative error minimization. We kind of nudge the initial concentrations of this chemical species and compute the forward trajectory and see how well they match up with the satellite observations and go from there. And then at the end of this minimization process, we'll get kind of the optimal analysis trajectory. And again, 4D VAR also, as opposed to 3D VAR, will incorporate multiple satellite observations from future time steps, whereas 3D VAR will only consider kind of observations or will kind of yeah, consider observations at the time step of the initial concentrations. This is the cost function that the minimization algorithm wants to minimize. And the cost function and this might be a simplified version, includes a term for the model error as well as the observation error. And I won't go too much into the math, but we want to find kind of the initial model concentrations x0, which um, bring the gradient of the cost function as close as possible to zero. And computing this gradient involves matching the observations that are at future time steps from the initial model field to the initial model field. Stepping, this means that we have to compute um, how changes in the initial kind of model concentrations will impact concentrations at future time steps. And this part I've been struggling to kind of find the best way to explain this, but if it's not clear, feel free to ask more questions at the end. Um, but the gradient involves computing kind of a series of these M matrices um, at each kind of time interval to compute, um, and each of these M matrices gives us how um, chemical species will respond to perturbations in concentrations at the previous time step, and termed the tangent linear model. And the transpose of this used in the gradient computation is called the adjoint. And while the adjoint has been used in chemical data assimilation studies so far, it requires a lot of extensive development work. Adjoints need to be computed for every update of the chemical mechanism, and it also requires around 5 times the computational resources of a chemical transport model Ford run. Um, Now, some prior studies have looked at kind of replacing the full adjoint of geochem and doing 4D var after replacing it with no adjoint and also an advection-only adjoint. And this did result in worse performance than the full adjoint, including the chemistry, but did still represent an improvement over 3D var. And other works have also tried linearizing neural networks to compute approximate adjoints for different applications such as gravity wave drag parameterization. And so but there haven't been any studies that I've seen so far that use machine learning to try to emulate the adjoint for chemical data assimilation. So this is what we have been trying to do. So getting into the training data for yeah, our ML model. So we kind of got the chemical states from the GOCF model, includes concentrations, reaction rates, and also some meteorological data. The domain is a very small but representative subset of chemical conditions and seasons and locations um, in the GOCF domain for a total of 37,000 total initial conditions. And credit to Obenstern for developing this data set. Um, with this data set, we then ran the data set through a standalone box model of the KPP mechanism that's used in geochem. This generates code to solve the system of differential equations that represents the chemical mechanism of geochem. And yeah, Open also thankfully kind of made this box model very easy to use. And so we run it once with the original concentrations, and then we run it another time after perturbing the initial concentrations by a certain amount here, using the example of NO2, and then using both of the output concentrations, we compute um, the change in the output NO2 with respect to the input NO2 perturbation. Um, and this will be, I hope, I'll try to make this a bit more clear here. So we have kind of the original trajectory of the box model over one time step, and then we bump the NO2 up and run the box model again in order to compute the gradient over one time step of NO2 and other chemical species. And just to shout out that this box model has been used for quite a few other applications because um, sorry about that. It's easy to use and tinker with. So yeah, like students in Sam Silva's group at USC have used it to study timescales of chemical cycles in the geochem mechanism. Oben's been working a lot on speeding up twilight chemistry with this box model, and also, yeah, as Daniel mentioned, learning chemical mechanisms with graph neural networks as well. So for our initial evaluation, we're going to focus on NO2. As you all know, it's involved in key reactions in the atmosphere, and it also rapidly reaches equilibrium with NO. It's highly relevant for air quality applications. And also NO2 rapidly reaching equilibrium with NO enables us to kind of benchmark the NO2 gradient in geochem using the Layton relationship shown here. It's been used in other kind of data assimilation-based reanalyses, such as the CAMS model using the ECMWF. Um, it kind of it yeah, it's approximates the ratio between NO2 and NOx, and we use it as an approximation of the amount of perturbed NO2. Say we add 1 parts per billion of NO2 at T, how much of that NO2 will remain NO2 at T plus 1, and how much will be kind of reacted away to other species. And this enables us to kind of get a chemically based baseline for our machine learning models to compare against. So first of all, some results that I've shown before about how well a latent relationship can capture NO2 gradients. Prior work on the latent relationship has found that it holds in steady-state conditions, but doesn't do too well in conditions where there's rapid changes in light intensity, such as twilight, and also places with significant emission and deposition, such as urban areas. Um, and so this kind of gives us expectation of how well latent will perform. So yeah, we perturb NO2. The results I show now will be after perturbing NO2 by 5 parts per billion. And so overall, we found that during daytime, Layton gives a strong overall approximation of NO2 gradients. And the plot on the left graphs the RMSE of the change in output NO2 given a 5 parts per billion perturbation to the input NO2. So the unit of RMSE here is parts per billion. And on the right is the kind of mean percent bias for the change in output NO2. Yeah, and again, it shows that except for the upper stratosphere at the surface, Layton does quite well for daytime with low bias. But at specific locations with more unique chemistry, Layton struggles a bit more, such as in Beijing, which is quite crazy as you guys might have seen in your studies, and also Amazon. In the Amazon, Layton underestimates NO2 gradients at the surface. Also, as we expected based on the literature, Layton performed a bit worse during twilight than during daytime, especially at the tropopause. So we saw that Layton does well for kind of for daytime NO2 and places with kind of consistent NO2 chemistry, but struggles a bit more in areas with chemistry that's not represented in the latent relationship as we might expect. So we then trained an XGBoost model to compare against the latent relationship. Um, it has great predictive capability and it's also relatively interpretable and it's very efficient. And this is why we used it. Um, the input data were the variables used in the latent relationship. Mhm. And we trained it to again predict the um, change the NO2 gradient over one time step. And we found that the XGBoost is able to capture the NO2 gradient better than Layton in the upper stratosphere and at the surface, but in other kind of model levels, XGBoost actually does a bit worse than Layton um, for daytime. And then during twilight, XGBoost does improve on Layton for most model levels. So yeah, we can see here that Layton again performs quite strongly for areas with chemistry that's kind of consistent or not too unique, but XGBoost improves during twilight um, and at the surface. So we then applied, so then we kind of wanted to evaluate how Layton and XGBoost both do on the global grid. So we perturbed the full kind of GOCF model at the full resolution and global domain, and then compared Layton and XGBoost against the GOCF ground truth instead of the kind of the KPP box model ground truth or the small input data set that we've been using. Again, we applied the XGBoost model that was trained on just 16 sites to the full global grid. And this might not be the most kind of or we didn't expect XGBoost to generalize perfectly, but it actually did pretty well. And yeah, this plot was just for illustrative purposes, but oh, before I go on, I'll note that the scale is from 0 to 1 because the lowest possible value for the NO2 gradient is 0, and the highest value we see is 1, where 1 means that all of the NO2 perturbation at time t remained as NO2 at time t plus 1. And so the dark areas in this kind of plot show areas where most of the perturbed NO2 is removed, whereas light or yellow areas show where perturbed NO2 remains NO2 over one time step of KPP. So there's a lot going on here, but overall, we see that while on kind of the global scale, latent and XGBoost both perform relatively similar compared to the GOCF perturbations, we see that XGBoost does reduce bias of gradient emulation in kind of regions we might care more about. So for example, over Eastern China and over Shanghai here, we see that XGBoost does a better job than Leighton. And again, this is just one example, but um, yeah, the plots across different seasons show a similar pattern. And over on the right, we have the relative error for XGBoost and Leighton compared to the geoslopes. And we see that both have some bias in over Antarctica and also over open ocean. But these are areas with very low NO2 concentration, um, more sensitive to perturbations, and perhaps less relevant for kind of data assimilation or health impact applications. And again, we see that also over the Amazon, XGBoost is able to kind of improve on Layton's representation of the NO2 gradient. And um, yeah, again at the Amazon over a so the previous slot was for January and even in the summer as well. XGBoost does reduce bias over um, Amazon, whereas Layton has a pretty significant underestimate of NO2 gradients. So we saw that XGBoost is able to improve on our chemical baseline, especially for the regions we care about. Um, but we also wanted to look at other chemical species that might have that are significant for data assimilation applications. So we looked at ozone as well as isoprene. And for ozone, um, we saw that overall XGBoost accurately emulates ozone gradients, except over Beijing and also over the tropics and other urban sites at twilight. So for ozone, we removed the stratosphere from our training because the like huge difference in ozone chemistry in the stratosphere versus the troposphere. Um, so hence there's only three model levels, the surface, and then the remainder of the troposphere. Um, and then these plots show kind of the absolute error or yeah, the error in gradients, gradient predictions of XGBoost as compared to the KPP standalone box model. And so Ozone XGBoost does a great job over all the sites, except has a pretty significant S overestimate over Beijing, overestimate over Borneo in the upper troposphere, and then underestimates in two urban areas, Kinshasa and Los Angeles. And so again, similar to NO2, we see that XGBoost is struggling to capture the chemistry where it's more unique. And for ozone as well, we these results show we've tried a bunch of different feature combinations, but this result is for XGBoost trained with all of the species and all of the reaction rates in the GOCF kind of output file, so all 290 species and 930 reaction rates as compared to the six variables we were using for the NO2 XGBoost. And then applying the ozone XGBoost to the global geos grid, we find that here the XGBoost does a good job of capturing the overall ozone gradient distribution, but it kind of smooths out the lows and the highs of the gradients from GOCF. So, for example, um, over eastern China, we see a larger area of low ozone slopes from the GOCF model than from the XGBoost. And yeah, for XGBoost, we don't have a, or for ozone, we don't have a steady state kind of assumption to compare our XGBoost model against. But yeah, overall, again, we see that it does capture the spatial kind of distribution of ozone slopes quite well. And again, just more kind of illustrative examples that show the overall performance of XGBoost for ozone. It kind of smooths out the tails over kind of Brazil here and over land in general. but does a good job of capturing like the kind of areas with low gradients regardless. Um, I think I misplaced the boxes here. But again, yeah, this kind of showing the underestimate over Eastern China as well. And yeah, there's some more interesting kind of spatial features like this underestimate over specifically Nepal that I haven't gotten a chance to dig into specifically yet. But yeah, might be worth probing in the future as well. And kind of lastly, for the set of results here, we also tried training XGBoost to predict isoprene slope, and we found that the XGBoost overestimates isoprene gradients over urban areas and then underestimates gradients over remote areas, such as Cape Grim and the Ozarks in Missouri. Um, and oh yeah, again, overestimates over Beijing, LA, and Paris. Yeah, these I haven't looked too much into isoprene results yet, but XGBoost does show a decent amount of skill at predicting, although I think it requires it, yeah, it does not do as well as for NO2 and ozone. So yeah, that was just the kind of overview of um, the main results I've been working on the past year. Again, we found that the steady state assumption, the latent relationship, is competitive with XGBoost for predicting NO2 gradients at most sites and levels during daytime, but XGBoost improves on latent for areas with kind of more unique chemistry, such as during twilight and over urban areas and the tropics for approximating NO2 gradients. And XGBoost captures ozone and isoprene gradients to a lesser degree, except again in kind of unique chemical conditions. Um, so yeah, we believe this set of results shows that XGBoost shows some promise in emulating GeoCF chemical gradients, even with, for example, for NO2 with a very limited subset of features towards enabling full-scale chemical data assimilation. And yeah, I think kind of the two big next steps to kind of evaluate whether this method could work in a real scenario is trying to integrate XGBoost into data simulation testbed JEDI that NASA has been working on for GeoCF, and also to evaluate kind of the impact of approximating the adjoint on longer timescales beyond just the one time step shown here. But yeah, we've kind of found that trying to integrate this XGBoost model into JEDI would require a lot of kind of um, computate like coding legwork. So we haven't been able to do that quite yet. But yeah, so but I think those are kind of the big next steps. And yeah, so that was it for results here. Yeah, I just want to thank Christoph Keller and Julie Nicely for kind of mentoring me throughout the past year. Peter Ivan and Michael Long as well, who kind of helped me bounce around ideas, and Oben Stern for providing the box model and kind of encouraging me throughout the year as well. And yep, as Oben said, I just started in Alex's group at UW, so yeah, looking forward to connecting with you guys. And yeah, I think I'll be staying in the chemical mechanism emulation space for a while longer as well. But yeah, thank you guys for listening. Happy to take any questions or thoughts or feedback too. So yeah.